Oh, that's funny. That's really funny.
Hi, everybody. The plan for today. We're going to do 13, 1, and 2. Give yourselves a little congratulations, though. You've made it through the portion of this class that is new. We're now going to be entering into recycling some topics from Algebra 2 and just looking to add a little bit of depth here. So you will be starting to see things that look familiar, ideally that you've done before, just recircling to pick up a little bit extra mastery and maybe probe a little bit deeper in a couple of different situations. So that's the plan. So in section 1, we're going to be talking about polynomial or graphs of polynomials, but polynomials in general. So let's say that this is our graph of our polynomial. There's a few key features that we want to be able to talk about when we talk about the graphs of polynomials. So I'm just going to kind of vocab this with a picture rather than writing things out. So you have those points, which we call zeros, or maybe we call them x-intercepts, or maybe we call them roots, or even we can call them solutions. We got like these guys right here. Those are extrema. And there's actually 4 different types of extrema. There's local maxima and local minima. And there's absolute or global maxima and minima. Now, if I'm talking about this one, what type of extrema is that guy that I highlighted? Local or absolute, though? Local, very good. Because if I take just like its little area, it's the tallest point in that area. But if I extend it big enough, eventually we see, there's stuff taller than it, right? So it's not the king of the hill, but it's, the big fish in the small pond, right? But there's still some whales floating around in the ocean that are dwarfing it. So this other one, what's the other one then? Very good. Is that okay? And then there's these parts. Those are called the end behavior. And in this course, we're going to describe this end behavior using a different notation than maybe you've been accustomed to. I'm going to start by translating what you're looking at into the notation rather than just like explaining, and then explain what the notation means. But I think that's usually the easier way to approach it. So if I look at the graph of a polynomial, it's going to have 4 possible end behaviors. So you're going to have either that left-hand arrow, and that left-hand arrow might point up, or it might point down. Oops, and I wrote them. I'll just do it so it matches. And then the same for the right-hand arrow. And I regret the spacing that I've chosen, so I'm going to just kind of fudge that a little bit. So those are visually what you're looking at, right? Does that feel okay? Either we're going to look at the left arrow and look at if it's pointing up or down, and the right-hand arrow and look at if it's pointing up or down. Jacob, get out of jail free card for you, or early anyway. So the way we're going to write this then on our sheet of paper is we're going to say the limit as x approaches negative infinity of f of x is equal to positive infinity, and then the limit as x approaches negative infinity of f of x is equal to negative infinity, and the limit as x approaches positive infinity of f of x is equal to positive infinity, and the limit as x approaches positive infinity of f of x is equal to negative infinity. So symbolically, these are saying the same thing as what we said when like the right arrow points up or points down or whatever. And if you notice, these are almost exactly the same looking thing, right? There's just some negative signs that are in different places. So when we're talking about the left arrow, the negative sign is on the infinity. If we're talking about the right arrow, it's a positive sign on that infinity. If we're talking about up, it's a positive sign on that infinity. And if we're talking about down, it's a negative sign on that infinity. Does everybody feel good about the pattern going on? So if we go back and I look at my graph, if I look at this arrow, that's the left arrow pointing down. So that's the end behavior that I would write. Does everybody feel okay there? Where we just have these four names and we're basically matching them to the picture, right? That's ostensibly all we're talking about doing. So that symbolically what that says is LIM, and then underneath it you have X arrow, and they'll be either positive or negative infinity. At the same level as the LIM, you're going to write f of x equals, and then positive or negative infinity. Is that okay? Did you use that notation last year or no? Yeah? Excellent. All right. So when it comes to finding these locations on a for a function, we most likely aren't going to do that by hand, specifically the extrema. In fact, right now, algebraically, we don't have a good way to do that by hand. Some of the times the zeros we can find by hand or the end behavior, that's not a problem. But if I'm looking for extrema, that's a can't do that by hand type of problem. How are we going to do that? With our calculator. In fact, we're going to do the zeros with our calculator also here, so I can show you guys again how to do that. So I'm going to start by inviting you, if you have your calculator with you and you want to follow along, to take that out. If you just want to sit and watch, or you don't have your calculator with you, or if you want to borrow one, I got a stack on my desk. If you just want to borrow, that's cool too. Whatever floats your proverbial boat. All right, so I'm going to start by turning my calculator on and going to the y equals menu, so that upper left-hand corner button. I'm going to clear out anything that's in there. So I had a couple of guys in there. And then I'm going to type in my function here, x cubed minus x, and I'm just going to put that into y1. Now, I don't know about you, but lately I've been having all kinds of cuckoo crazy windows on my graphing calculator because I've been looking at these scatter plots and stuff. Who knows what it's been set at recently? If that's the case, I'm just going to, instead of just hitting the graph button, I'm going to pick zoom standard. So I'm going to press the zoom button and pick Z standard. That just resets my window to a sensible window. And if I look at this guy, okay, well, this is a little far away for me to see really what's going on along the x-axis and what's happening with, like, it appears maybe there's a local min and max here. So I'm going to get a closer view of that. Now, to get a closer view of that, you can either use the zoom in functions with your calculator if you want. I don't like doing that. I like to have a little bit more control than that. So I'm going to pick the window myself. If I look at this picture, it seems like by, all of the action is happening between like -3 and +3 on the x-axis, and maybe -2 and +2 on the y-axis. You guys buy that? Or thereabouts. So what I'm going to do is I'm press the window button. I'm going to change my x min and x max to reflect that -3 to +3 window we just discussed, and change my y min and y max to reflect that -2 to +2 range we just discussed. Everything else I'm just leaving whatever this default setting is. If I hit graph again, that's a much nicer looking picture. I can definitely see what's going on there now. So I see I have 1, 2, 3 zeros and 1, 2 local extrema. You guys see that? Let's find the zeros first. To find these with my calculator, I'm going to press second and then the trace button. The trace button's there up on the home row. Which command sounds like the one I want if I'm looking for zeros? The 0 command. Good job. You're using your head now. So the calculator is going to ask me 3 questions here at the bottom. They're always going to be the same 3 questions. It's going to ask me for a left bound, a right bound, and a guess. So if I'm, say, looking for this 0 on the far left, I need to start by moving my cursor using the left and right arrows so that it's on the left-hand side of that x-intercept. So that looks good. I'll just press enter. Now it says that give me a right bound, so I'll use my left and right arrows to move my cursor so that it's on the right-hand side of that x-intercept. Press enter again, then it asks for a guess. You don't have to move it anywhere. If there's only one x-intercept in between, the guess doesn't really matter, so I just pressed enter again. And there it spits out my next 0, or my 0. Now we have 2 more to find. Can you repeat that same process to find the other 2 zeros on your own? Give it a try, those of you with your calculators out. When you do that, those are the zeros you should get. I'll pause here for a moment for those of you trying it out on your own. All right. Anybody have any problems doing that was trying it? Excellent. Next thing we're going to do is find our extreme. If I look, I see I have 1, 2 extreme. One is a local max, the other is a local min. Let's find that maximum first. To find that maximum, we're going to press second and the trace button. Which of the commands here sounds like the one I want if I'm looking for a local maximum? The maximum command, oh my goodness, it's so... You probably did. Yeah, it's going to ask us the same three questions, left bound, right bound, and guess. So I'm just going to make sure my cursor is on the left-hand side of that maximum. That looks good where it's at. Right bound, I'll move over to the right-hand side of that maximum. Press enter. Guess, it doesn't matter as long as it's in between. So there's my local maximum at negative 0.577, positive 0.385. Yep, there's some on top of the file cabinet. And then can you guys try to find the local minimum for me? Use your calculator. Try to do that on your own. I'll write in the answer so you can check. Anybody have problems finding that local minimum on your own? Should have been pretty easy, especially if you've done this before, right? All right. Fantastic. So the next question might be, okay, I found 3 zeros and I found 2 extrema. How do I know that's all there was on that function? I'm not sure I do know that was, I mean, I looked at it, but like, I didn't look at the whole thing, right? It goes on forever. How do I know it doesn't do something else later on? Well, where am I? There's what I was looking for. We have a little theorem to help us here. So this theorem says for a polynomial of degree n, we'll have at most n zeros and at most n minus 1 extrema. When I say the degree, remember that's the biggest exponent, right? So just a quickie little example. Ooh. All right. So for the function f of x equals 3x to the fourth minus 5x cubed plus 2x plus 2, how many zeros could there be? How many extrema could there be? Before I start, I want my degree for the polynomial f of x. What is the degree for this polynomial? 4, just the biggest exponent. So how many zeros can there be? Close. At most 4, which means I could have 4 or 3 or 2 or 1 or 0. Doesn't matter which way you write it, but if you don't have at most there, you have the wrong answer because you've neglected the possibility of it having other possibilities, right? Is that okay with everybody? So again, I'm going to be picky for that at most. So you really got to read the question and make sure you're answering it correctly. So if I want extrema now, how many extrema can I have? At most 3. Good, or you could write 3 or 2 or 1 or 0. But I'm going to stick with at most because I'm into that whole brevity thing. Right? Imagine if it was a degree 10 polynomial. It's like, oh my goodness, I'm not writing down all those possibilities. Just let me say at most and get on with my day. I have better things to do than listing these numbers over and over and over again. All right. Everybody feel okay here? There's a big load of nothing basically going on, right? Bunch of recycled ideas and some vocabulary. Using the calculator, that was no big deal. In section 2, we're going to talk about finding zeros for our polynomial function. And really, we're going to do that today algebraically by factoring. So before we get going, I just want to list out some of the factoring techniques that you guys should already be familiar with that we're going to kind of review here in a moment. So you have the difference of two squares. I've abbreviated that as DOTS, difference of two squares, i.e. a squared minus b squared is equal to a plus ba minus b, right? You have the sum of two cubes. You have a difference of two cubes. We have trinomials in the quadratic form. Where a is equal to 1. We used one method. And we can also do this with trinomials in the quadratic form, where a is not equal to 1. We have a different method for that. This is basically the short cut. This is the long way. You have factor by grouping. And, of course, the good old standby, greatest common factor. GFC is like Gordon Food Service or something. So when I teach this, what I like to do is build out a flow chart to help us work through some of these more difficult factoring problems where we might have to use multiple of these methods inside of the same factoring problem. So that's what I'm going to do now. My advice to you would be to start a new sheet of paper and turn it landscape style, because this gets kind of big. And if you want to make sure you have a space to do it, I don't want you to run out of space or whatever if you're a notes person. If you're just going to look at my notes, though, like whatever, or if you're in OneNote doing this, like you have infinite space, so like no biggie. So the first thing we do is we check for a greatest common factor. Oops, did it again. And then we're going to look at the number of terms. And we're going to consider situations where you can have 2 terms, 3 terms, or 4 terms. If there's 4 terms, you're going to check to see if you can use factor by grouping. If the answer is yes, then you need to check each factor down the 2-term path. If it's no, then you're done. If you can't do factor by grouping on 4 terms, there's nothing left for us to do until we add some of these additional methods here that you'll probably remember and be like, oh my God, I hated this. So if it's 3 terms, we're going to check to see if it's in the quadratic form. If it's not, well, then there's nothing else we can do with that guy, at least for now. If it's yes, we want to look at that leading coefficient and see if it's equal to 1. If it is, we're going to try the short method. If it's not, we're going to try the long method. If the short method works, we're going to factor it, and then we have to check each factor down the 2 terms branch. If it's not factorable, then we just stop. There's nothing else for us to do. And the same thing with the long. Again, if it's factorable, we have to check our factors down the 2-term branch. And if it's not factorable, then we can just stop. There's nothing more for us to do with that. Okay. Now we'll build out the very important 2-term branch, because you notice that anytime I'm able to do any other kind of factoring, I would have to check it down the 2-term branch. So this one is really important. So the first thing we're going to check is it a difference of 2 squares? If it's yes, we'll do that factoring, and then what do we have to do? We have to check those factors down the 2-term branch. If it's not, then we're going to check, is it a sum or difference of 2 cubes? If it's yes, then we have to check those factors down the 2-term branch. If it's not, then we can stop. Yes, Cameron. Sure. I'm going to zoom that out so you guys can see the whole thing there at one time. And now I'm going to do a couple of examples while I show you guys how I navigate through this flow chart to do the examples. Sound good to you guys? Yeah. Okay. So I'll start with an easy one, and we'll get like progressively a little bit more difficult. We'll do like 3 of them. Again, this is a skill that I think that we've done probably a pretty good job of before. So I don't want to belabor the point too much, but you know, it's good to get some practice here. All right. So the first thing we're doing is looking for a greatest common factor. So if I have f of x equals x cubed minus 6x squared minus 8x, is there anything in common with each term of that polynomial? And x. So I'll go ahead and factor that out. Well, actually, before I even do that, I'm going to just set it equal to 0, right? If we're looking for zeros, we said that's kind of the same thing as a solution earlier. So now I'm looking at the piece that's left. So how many terms are there in x squared minus 6x minus 8? Three, right? There's the x squared, there's the 6x, and then there's the 8. That's 3 terms. So far, so good. Next thing we'll ask, is it in the quadratic form? Is the degree of the first term twice the degree of the second term and the third term a constant? Yes. So then we'll look, is the leading coefficient equal to 1? Yes. Oops, I should probably have yes here and no over there. Since it is, we're going to be doing the short factoring. Oops, and this has a typo in it. Let's make that plus. So are there 2 numbers that multiply to give us positive 8 and then add to give us negative 6? Multiply to give us positive 8, add to give us negative 6. Negative 4 and negative 2 is correct. With that, that's all I need to get to my factored form. If you have to do the long way, you have to break it up and do grouping, and it's kind of a whole thing. Okay. Now, so we did that. Now we have to go to the 2 terms. So I'm looking at x minus 2. Is that a difference of 2 squares? No, why not? Because it's just x to the first, right? It's not something squared. Okay, is it a sum or difference of 2 cubes? No, man, because it's just x to the first. It's not something cubed. So we can stop. We do the same thing with x minus 4. We're going to get the same result, right? So we're done factoring this thing. So now I can apply the zero product property and set each of these factors equal to 0 and solve. Well, x equals 0, that's done. I add 2 to both sides and add 4 to both sides. So I end up with the 3 zeros as follows. Does that feel okay there? Okay. Move you out of the way so we can do another example and still look at this. So let's say we're looking at 2x to the 6th minus 128. Again, first thing we're going to do is look for a greatest common factor. Did you guys see anything in common between 2x to the 6th and 128? 2, right? So I can factor that 2 off. And at the same time, I'm going to set this equal to 0. I'm just going to combine those first two steps. Okay, if I look at the number of terms, how many terms do I have here? 2, right? I have the x to the 6th and the 64. Everybody agree? Okay. Is that a difference of 2 squares? Oh, you guys, yes it is. Look, x to the 6th, you're saying is not, because it's not something squared, right? But isn't x to the 6th x cubed squared? If it has an even exponent on it, you can definitely make it something squared, right? Everybody's okay with that? If you see a binomial thing with an even exponent, you should be thinking, well, this is quite possibly a difference of 2 squares. I got to really investigate. Hopefully we saw 64 was 8 squared. That's easy to see, I would think. Okay, so if I do my factoring pattern, then I'm going to have x cubed plus 8 times x cubed minus 8. But now we have to check those down the 2-term branch. So x cubed plus 8, is that a difference of 2 squares? No, right? Because it's cubed. It's an odd power. It can't be square. It can't be a perfect square. So is it a sum or difference of 2 cubes? Yes, right? So obviously x cubed, but 8 is 2 cubed. And then obviously we can do the same thing with the minus 8, right? Everybody okay there? So if I apply my sum and difference of 2 cubes factoring patterns, I'm going to have x plus 2 times x squared plus, minus 2x plus 4, and then x minus 2 times x squared plus 2x plus 4 equal to 0. Put a little border there. But now we have to go to the 2-term guys to check these again. So I'm just going to be checking x plus 2 and x minus 2. So is it a difference of 2 squares? No. Is it a sum or difference of 2 cubes? No. So we're done. Is everybody okay there? Why am I not bothering to check the trinomials down the 3-term branch? Why don't I have an extra step there and suggest we have to check those as well? So if you remember, those guys always have imaginary solutions, so they're not going to be factorable over the reals. The trinomial parts of your sum and difference of 2 cubes always have imaginary solutions. They are not factorable over the real numbers. So we don't have to worry about them. And because of the way we've structured our flow chart, because we're always checking the difference of 2 squares before looking for our difference of 2 cubes, we'll always have a situation where there's not another, unfactorable trinomial mixed together with it. So we don't have to worry about it. By design of our flowchart, we can avoid that. If we had done this same problem and done the perfect cubes first, or the difference of cubes first, you end up with something you can't deal with afterwards, and it's a problem. So by design of our flow chart, we don't have to worry about that possibility, which is nice. Okay, so we got these guys. Then we take each factor and set it equal to 0. Now, 2 is not equal to 0. That has no solution. I have x equals -2. As we just discussed, those trinomials have no real solution. So this guy has only the 2 real zeros of -2, 0 and +2, 0. Now that's a tough one, right? There, the flow chart really kind of helps out keeping track of kind of what we still need to do, where we're at in the problem, right? That makes life hopefully rather helpful. All right, let me, again, I'm going to scoot this over. Come on, you stupid thing. All right, we'll do one more. Sound good? All right, so we have x to the 4th minus 13x squared plus 36. So greatest common factor here. No, right? Everybody agree? If I look at the coefficients, 1, 13, and 36, nothing in common there. If I look at the variables, x to the 4th, x squared, then a nothing. Okay. Number of terms we have is 3. Is this in the quadratic form? It is, because the degrees are 4, 2, and then constant. So the first degree is 2 times the second degree, and then we have a constant stuck at the end. So this is quadratic form. The leading coefficient is equal to 1, so we're still going to do our short factor here. So I need 2 things that multiply to give me positive 36 and then add to give me negative 13. Good, -9 and -4. Great. So I know that it's going to look like this, but what goes here? It's not x, it's x squared. Yeah, did you guys see that? So like whatever the degree of this term is going to be the degree here, right? Okay. So now we got to go down the 2-term branch. Is x squared minus 9 a difference of 2 squares? Yes, it is. Ooh. Is x squared minus 4 a difference of 2 squares? Ooh, yes, it is. If I go down and I check each one of these, what do I notice about each one of the factors remaining? They're all degree 1. So they can't be differences of two squares. They can't be sum or differences of two cubes. So we're at a finish here. Is everybody okay with me just kind of hand waving there at the end? Once you see degree 1 terms, you know you're done. So we get 3 and negative 3, 2 and negative 2. So those are my x-intercepts, or my zeros. How do you feel there? Okay. I got one more definition and then 2 more examples, and then we're going to be done. So this definition is called a multiplicity. And I'm going to just kind of do this by example. So if I have something like x squared plus 6x plus 9 equal to 0, and I want to solve this, does this factor? What does it factor to? X plus 3 times x plus 3, right? So if we set those equal to 0 and solve, my solutions are negative 3 and negative 3, right? How many solutions do I have here? Well, look at the actual problem. There's just one solution, right? The solution is just negative 3. But because negative 3 occurs twice, we'd say that it has a multiplicity 2. So we'd say the solution there is negative 3 multiplicity 2. Now, if I got an answer 3 times, what would we say? As multiplicity 3, and so on and so forth. Is everybody okay with that? Now, multiplicity is actually quite helpful because it has a graphical analog to it. So let's say that we have f of x has a 0 at x equals a. So there's kind of 4 different ways that x-intercept might look. That is a thick mama jammer right there. Let me go back and get like a normal size pen. Okay, could look like this. Could look like that. Or it could look like that. So in this first situation, we call this a straight because the graph is passing just straight through the x-axis, right? Looks like a straight line going through. So if that happens, I know the 0 or the solution x equals a has multiplicity 1. This second situation where it looks like it hits the x-axis and then bounces off of it is called a bounce. If that's the situation, then x equals a has an even multiplicity. That solution could be used 2 times or 4 times or 6 times or 8 times. I don't know how many times is the top limit, but I know it's going to be used at least 2 times. Everybody's okay with that? And it has to be an even, so it couldn't be used 3 times or 5 times or whatever. This last situation is called a bend. You see how it's like changing concavity there? So x equals a has a multiplicity of 2k plus 1 greater than 1, all right, which is odd, but greater than 1. So that, if you see a bend, that solution is going to be used 3 times or 5 times or 7 times or 9 times, some odd number of times. I don't know how many, but I know it's going to be not even. I know it's going to be more than once. Is everybody okay with this? Did you do this last year when you did this in Algebra 2? Do you remember multiplicities and bend, bounces, and straights? Maybe? Okay. Can be really helpful later on when we start dealing with higher degree polynomials or polynomials with terms more than 4. Yes, sure. I got 2 more examples and I'm done with you guys. So this next example is kind of like, this is kind of problem is called an optimization problem, because you're looking to find the best way of doing something, the optimal way of doing something. It says that a company wants to create a cardboard box with an open top. So you know what that, you can picture what that looks like in your head. Like when you take the cover off like a board game, it's like an open top box, right? The box needs to have a volume of 500 cubic inches and is to be created by cutting squares from each corner of a rectangular piece of cardboard in order to create tabs to fold up. The piece of cardboard is 26 by 20. What size squares should be cut from each corner in order to create the proper volume? Okay, well, let's just draw a picture here to start. Kind of what it's describing. So we're going to have some rectangular piece of cardboard. And then out of the corners, we're going to cut these squares out, right? So that when we fold up along those perforation lines, we end up with a open top box, right? So the question it's asking is what size squares? So I'm going to label those as X, and that's what we're looking to find. And we're told the volume needs to be 500 cubic inches, right? So remind me again, who remembers from geometry what the volume of a box is? What's the formula to find that? Come on, guys. Will Hannah knew second hour. If Will remembered, somebody in here's got to remember. Length times width times height. Everybody's okay there? All right, so let's look at our picture and figure out where the length, width, and height are going to be. So like we're going to fold along this edge, right, to create part of our box. Well, that's going to be the length. You guys can see that? And then we'll fold along this edge, and that'll be the width. And then like this edge here is going to be like the height, right? Because that'll be coming up out of the plane, right? Does everybody feel okay in picturing this thing in 3 dimensions where the length, width, and height is? Okay. What I want to do now, since I want to solve for x, is I want to rewrite the length, width, and height in terms of x's. One of them is super easy. Which one is the easy one to write in terms of x? Guys, it's the height. What is the height in terms of x? It's just x, right? Because it's just the side length of the square, which we said was x. That's great. Piece of cake. All right, let's look at the width then. I know from here to here is 26, right? But I'm going to take away this piece and this piece. So what do I have left? 26 minus 2x, right? Because I'm taking away x and then taking away x again. That's 2 x's. Everybody agree? What's the width going to be? (20 minus 2x). Everybody feel, you see that? So we're left then to solve the equation. 500 has to equal 26 minus 2x times 20 minus x times x. Now, if I wanted to try to solve this by hand, I'd have to FOIL this all out, subtract the 500 over to the other side, see if I can try to factor this thing. That all sounds like a colossal nightmare to me because I don't even know that this is going to come out to be a factorable polynomial. I'm not going to do any of that. I'm going to solve this by graphing. What I'm going to do is I'm going to just put this into y1 and this into y2 and find the intersection. That seems like a much better route to me because I'm guaranteed to get an answer out of this. But before I do that, I want to think about the window. What are my possible values for x? What do I know about the side lengths of a figure? What values can they not have? They can't be negative, right? So if I have an x here, I know x has to be greater than or equal to 0, right? Is everybody okay with that? What's the biggest possible x I could have before I end up with a negative side length? I'll give you a hint. You want to look at the 20 minus 2x. What's the biggest value of x that we can have before we go negative? 10? Right? 2 times 10 is 20. Any bigger than that, 20 minus the bigger number is going to be negative. So this I'm going to use when I do my window. All right, let's get this in here now. So I'll go to y equals y1, I'm going to make 500. y2, 26 minus 2x times 20 minus 2x times x. Everybody feel okay there? Just copied it in. My window, I'm going to change my x's from 0 to 10. Those are only the feasible x's. I'm going to just leave that everything else the same. My y min to y max, I know I have to be able to see 500, right? Because that's what I put into y1. So my y min, I'm just going to make something a little less than 500, and my y max, I'm going to pick just something a little more than 500. As long as I can see y equals 500, I should be good. Everybody's okay there? Everything else stays the same. I'm just going to change the mins and maxes. Nothing else. Hit graph. There's my line for y equals 500. There's my volume function. So I'm looking for these 2 points of intersection, right? To find these intersections, I press second trace and pick the intersect command. Oh my goodness, Mr. Kulik. The calculator is going to ask me for 3 things. So it wants to know what 2 curves do I want to find the intersection and where should I start looking? First curve is the straight line. Press enter. Second curve is that tells me it's already been switched to the other one, so I'll press enter. Now I need a guess. Since I have 2 intersections, the guess kind of matters. So I'm going to move my cursor so it's close to one of them. That looks good. Press enter. So there's one solution, 1.20-ish. And then to find the other one, second trace, intersect command, enter, enter, first curve, second curve. And then my guess, I got to move over there and press enter. So 702. And that's all she wrote on this guy. Feel okay? All right, one last example and then we're done. Yup. Bye, skiers. Yeah, sure. So this is number 13 from the homework, just FYI. So it says to write a cubic polynomial with the zeros at 5, 8, and -1/2. If I have zeros at 5, 8, and -1/2, that means that I have solutions. X equals 5, X equals 8, and X equals -1/2, right? Everybody's cool with that? Since these are all equations, I can take the first equation and subtract 5 from both sides. And the second equation, I can subtract 8 from both sides. And the third equation, I can add 1/2 to both sides. Everybody feel comfortable doing that? Seems pretty obvious I can do that. If I look at that third equation, though, you know what I don't like about it? I don't like that fraction in there, right? So I'm just going to multiply both sides by 2 to get rid of that fraction. Everybody feels good? Now what I'm going to do is I'm going to multiply these 3 equations together. And since all 3 of these equations were equal to 0, the product of those 3 equations has to also equal 0, right? If I look at this now, since I have 1, 2, 3 x's that I'm going to be multiplying together, this is going to give me a degree 3 polynomial. And because the solution to each one of these separate factors is 5, 8, and -1/2, the resulting polynomial that I'm going to make is going to have solutions or zeros 5, 8, and -1/2. This is going to give me exactly what I want. I just need to FOIL this out now. So I'll start by multiplying the first 2 together. I'm just going to do that quickly in my head if you guys don't mind. And then to multiply these two together, I'm going to have to do like one of these guys. And then I just combine some like terms. So there's my cubic polynomial with the desired zeros. Basically just a foiling problem. You should have to figure out what three things to foil together, right? At this point, you guys should be able to do 1 through 15 for homeworks. I also have a delta math for this lesson. We'll have some time in class on Friday also to work on that, so you don't have to go crazy with it right now. It's kind of a big one. A lot of factoring practice in there. Because I'm guessing that, like, although we remember doing this, like, we're probably a little bit rusty at it. So, good idea to get some practice in. But that's where I'm at here. That's all I got for you guys. Any questions for me? Was it nice seeing some stuff that it's like, oh, I've done this before. This feels familiar and comfortable, at least, rather than new ideas.